Good afternoon. How's everyone doing? Good. Who's excited to learn about air quality today? Yeah, I got a clap. That's awesome. That's more than my last presentation. No, thank you for coming today. Thank you for the invite. Again, my name is Sean Nolan. I work for the Pennsylvania DEP, and we're going to talk a little bit about air quality and meteorology. Okay, and maybe talk about how the snowfall came to be outside. So as I stated, because of the Zoom issues, we're going to progress through the slides, try to progress through them fairly quickly. So next slide. So here's what we're going to be talking about today. We're going to be talking about why is air quality important, the history of air quality concern in Pennsylvania, why is there a concern of air quality in Pennsylvania, weather factors that influence air quality. So kind of like a meteorology 101 class. And then we're going to talk about specifically what we do for the Pennsylvania DEP and air quality forecasting and air quality monitoring in Pennsylvania. Next slide, please. So history of air quality concern in Pennsylvania. Next slide. So this is actually an image back from the 1930s in Pittsburgh. And that's actually not fog, that's smoke that was filling the city of Pittsburgh because of all the local industry in the city of Pittsburgh. Next slide. This is another picture taken from the 1930s, 1940s timeframe from the city of Pittsburgh again. And you notice how dark it is, other than the black and white, right? You notice how dark it is outside. A lot of the street lights are on. You can see how bright some of those lights are. Next advancement. This clock actually shows you it's around 12:10 p.m. So you can see how dark it was during the day in Pittsburgh. Next slide. Here are guys that didn't think they were getting enough smoke inhalation, so they decided to smoke a pipe on the corner of Liberty and Fifth Avenue in Pittsburgh. Again, that smoky scene of Pittsburgh. Probably many of us have heard about, right? I mean, have we heard about these types of scenes that were ongoing in Western Pennsylvania around this time, in the startup of the Industrial Revolution, and a lot of the facilities that were built right in the city, right near where people live, and they were emitting toxic pollutants into the air. Next slide. Again, here's a more vertical look at the city of Pittsburgh. Next slide. And this one's great. That big bright half circle on the left side of the screen, my right. The left side of the screen is actually the sun. And what you'll notice here are a couple things. If we click the next advancement, you'll notice that this was a pollution source right there in the city of Pittsburgh, and you'll notice the plume of emissions coming from that source. And what's interesting about this, it's not getting much loft, right? It's not getting much rise, and it's kind of flattening out. And so all that smoke that was being generated right there in the city was actually mixing back down toward the ground, which is what was causing that smoky scene in the Pittsburgh area. Next advancement. And there's that sun that I was talking about previously in next advancement. And then you'll notice that the flagpole at the top, you'll notice that the flag was not moving. So there's not much wind going on. And so this is one of the key factors we look at when we're looking at high air quality events in Pennsylvania, the wind flow, right? If we have high wind flow, we have a little bit more dispersion. If we have low wind flow, not much dispersion. And so you'll get what you saw here in Pittsburgh in the 1930s and 1940s, a lot of smoke building up in the city. Next slide. So, okay, so I touched on some of the weather factors that could be playing a role here, right? Light winds. Let's talk about this a little bit more in detail. Next slide. So historically specific weather conditions coupled with low-lying emissions have contributed to higher quality concentrations. The weather factors that typically lead to elevated air quality concentrations include, next, high pressure. There always seems to be this area of high pressure in place, and we'll touch on that in a second. Next, inversions. Okay, what is an inversion? All right, we'll talk about that. And next, stability, and this is what I was talking about with regard to the light winds. right? Light winds lead to limited mixing. And so in the case of Pittsburgh, those light winds were leading to a lot of the smoke being mixed back down to the surface. Next slide. Okay, so what is high pressure? Here's this Meteorology 101 class. As was stated in my bio, I graduated from this school. Penn State has a great meteorology program. I'll just say that. So we are. So we have high pressure, okay? And so what is high pressure? It's other than the big blue H you see on your local newscast. What does that high pressure mean, right? High pressure is associated with sinking air. So when we think of high pressure, we think of clear skies, right? A lot of sunshine, limited cloud cover. This is because the air is sinking associated with high pressure. The air actually flows out from high pressure to low pressure, and it's actually an interaction of and this is where some of the science comes into play, the pressure gradient force and the Coriolis force creates this clockwise flow. And so you'll see the diagram here, and I'm going to show you one of low pressure here and how that interacts with this. But you get the pressure force of winds out from the area of high pressure. The Coriolis force in the northern hemisphere turns everything to the right. So as it goes out from the area of high pressure, it's going to naturally turn that to the right. And so you get this natural clockwise circulation around areas of high pressure. And this is a key factor in determining where air pollutants are going to be heading. Okay, next slide. How does that converse with low pressure? Low pressure is an area of convergence. So that means when the area is coming in toward an area of low pressure, it is actually going to collide with each other and then rise. So we have a section of rising air, area flows in towards areas of low pressure. And again, it's the interaction of the pressure gradient force and the Coriolis force actually turns the wind in the opposite direction. As it's approaching the area of low pressure, it is actually turning to the right and actually forces the air going in a counterclockwise rotation around the low. Okay, so we now have a basis of high pressure versus low pressure and what that means. Next slide. So here, this is a general view of the United States and just a broad view of the synoptic weather flow in the United States. And again, we have there at the surface, we have a big H, a big blue H, a big red L, right? And you could see here on this diagram, it does a pretty good job at displaying exactly what that interaction is between areas of high pressure and areas of low pressure. Next slide. Here's another pictorial. I love pictorials. You're going to see a lot of pictures in this presentation. Areas of low pressure, you see that rising air. And so what that leads to, that rising air leads to that level of convergence. It leads to cloud cover development. It leads to rain showers. It leads to 3 inches of snow in State College, right? So we had this area of low pressure that came through here yesterday that created the cold air that was already in place, created the snow that you're currently seeing outside. But we kind of like the weather, when we look at high air quality episodes, we kind of like the weather dull, right? We like that area of high pressure. We like the area of sunny skies. Sunny skies allows the temperature to rise, right? It promotes the clear skies and that light winds environment. And so this is, once we see that area of high pressure, we're like, bing, 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 bing. Hey, we might have an air pollution, something going on with air pollution today. Okay, next slide. Okay, so talked about areas of high pressure. That was one of our 3 elements that we need for high air quality episodes. The next thing was inversions. Okay, what is an inversion? Anybody hear this term before? Am I just crazy? One person, 3 people, great, okay. So, no, this is great. So inversions, what is this? So there are multiple ways inversions can form, all right? You'll notice the pictorial on the left. The pictorial really explains it well. So you actually have areas of high pressure. Remember that areas of high pressure, there's clear skies, there's a lot of sinking air. What happens is that ground ends up cooling overnight. With no clouds in the sky, the heat that was generated at the ground level during the day is actually able to freely go back up to the sky, right? No clouds. The clouds kind of act like as this, I hate to say blanket, but kind of like a blanket, if you will, and hold the heat in. That's why it gets colder on clearer nights than it does on cloudy nights, all right? But inversions form when this air is able to radiatively leave the ground, and it actually cools the ground. And so what ends up happening is you get this warm flood of air aloft. And so how many of you know density of air? Did anyone understand like density of air? Like, okay, so cold air is more dense than hot air, right? So cold air, what does that mean? Cold air likes to be down toward the ground. More dense means heavier mass, right? And so it's actually down toward the ground, and the warmer air likes to be above it. And that's important because it doesn't like to move that way. The cold air likes to be at the ground, and if it's at the ground in these situations, it likes to be there. The warm air aloft, it likes to be there as well, and so it stays there. And so you get light winds. You don't get any mixing going on. And that's why inversions end up being a key role in high air quality episodes here in Pennsylvania. Next slide. So what can this do? It can actually cause interactions with different emission sources in Pennsylvania, like power plants, let's say, or local industry. And so it can cause different impacts on the actual plume and what the plume looks like, depending on that level of atmospheric stability that is ongoing. And this is just a few of the slides here, of a few of the cases here that happens what happens to the plume. Next slide. Okay, so we now have a basis for air quality forecasting, understanding some of the things with weather and how that relates, right? Let's talk about what we specifically do in Pennsylvania. Next slide. Okay. First off, we can't open up air quality forecasting until we talk about the Clean Air Act. And the Clean Air Act was enacted in 1970 due to increasing concern like what happened in Donora, Pennsylvania, not too far from, it's just south of Pittsburgh. The US Congress and the US EPA developed the Clean Air Act in 1970, and subsequent changes have been made to the Clean Air Act in 77 and 90. But the Clean Air Act focuses on 6 specific criteria, pollutants of concern. The National Ambient Air Quality Standards, as they're known for these pollutants, would be revised every 5 years based on the newest science. So essentially what happens is we have these 6 criteria pollutants. EPA revisits this 5, and knowing EPA, maybe 8 years down the road. And they look at the latest health science and say, okay, is there an impact to the health of all of the individuals in the US? Is there an impact based on this newer science? So this is done generally in that 5 to 8 year time frame. Next slide. So what are these 6 criteria pollutants? We're talking ozone. How many of you have heard of ozone? Okay. Particulate matter. Particulate matter, anyone? Yeah, okay. Nitrogen dioxide, sulfur dioxide, lead, and carbon monoxide. Okay, but for this talk next, we're going to be focusing on what's in blue there, the ozone and the PM2.5 specifically. Next. Okay, so what is ozone? I talked ozone. Some of you have heard about it. Ozone is actually a gas composed of 3 oxygen atoms, otherwise known as O3, if you see the shorthand. Ozone is a photochemical pollutant, which means photo means it needs the sunshine, and chemical means there's some sort of chemical reaction that takes place. So it actually needs the sun to complete the chemical reaction needed to form ozone. And the pollutants at which help to form ozone are nitrogen dioxide and nitrogen oxides like NOx, and volatile organic compounds, or VOCs. So essentially ozone is good in the stratosphere, right? How many have heard of the ozone depletion because of global warming, right? That's what they're talking about essentially. They're talking about the stratospheric ozone. But ozone is bad for your health if you breathe it in. The stratosphere is several miles up. The ozone at the surface can be very bad to your health. Next slide. Okay, so now we have a basis of ozone. Now, what is PM2.5? Okay, so if we look at PM2.5 is actually 2.5 microns in size. Is particulate matter 2.5 microns, What is 2.5 microns? Okay, this is a show and tell. So I want everyone to pluck a hair out of their head. No, I'm just joking. What I've done here is I've actually magnified the human hair for your convenience, okay? And this is what a human hair looks like. It's actually round, right? And so if we take a cross section of the top of that human hair, what do we see? We actually see it's actually a fraction of that human hair, okay? You can barely see a human hair, let alone see what size PM25 is, okay? So that just gives you some basis of what PM25 is. Next slide. What are the sources of PM25? We have things like wood burning stoves, forest fires, heavy duty diesel engines, natural sources, cars and trucks, non-road vehicles, leaf burning, and industrial sources, and some of these prescribed fires too, right? So we're going to focus on the forest fires, and we'll get into that in a second. But that's what the focus here is, on air quality impacts of what some of these prescribed fires can do too. Okay, next slide. Okay, PM is also composed of a mix of primary and secondary compounds. Next. So we have on the primary side, it can be directly emitted like suspended dust or sea salt, organic carbon, elemental carbon, metals from combustion, small amounts of sulfate and nitrate. Next. And then secondarily, it forms sulfur dioxide. When it mixes with sulfur dioxide, it forms sulfates. When it mixes with nitrogen dioxide, it forms nitrates. Ammonium can form ammonium sulfate, ammonium nitrate. And so there's a lot of science going on here in the atmosphere that you might not be aware of, right? Volatile organic compounds form organic carbon compounds that are in PM25. Okay, next. So we have the formation of PM25, and there's different ways it can form. It can form by coagulation. Particles sort of collide with each other, right? Next, condensation. We have a water droplet. It condenses, these particles actually condense in the water droplet and form a slightly bigger particle. Next, cloud and fog processes. Gases dissolve in a water droplet and chemically react, like the sulfur dioxide example and ammonium example, form ammonium sulfate. Next, and finally, there's a chemical reaction that could take place in our ammonium nitrate example. Okay, next. Okay, so we now have a basis of weather, all right? High pressure inversions, what they mean. What is ozone? What is PM25, right? So how does this all relate, okay? We use something we call the air quality index scale. And so we're actually measuring ozone and PM25 concentrations in the Commonwealth currently. All right. But the scales are different. They're different concentrations. PM25 is actually particles in the air, right? That can be collected on a filter. Ozone is a gaseous pollutant. And so what does that mean? It can be monitored out there, but they're on different scales. So we measure ozone in parts per million or parts per billion. We measure particles in micrograms per cubic meter, so a mass per unit volume, depending on how much volume that sampler is bringing in. All right. So we needed a way to compare, okay, how do you compare parts per million with micrograms per cubic meter? And that process is called the air quality index scale. Okay, it's a color code system where we can look at the air quality. And this was developed by the US EPA. And again, the air quality index scale is outlined by the severity of the health effects. Next slide. So it's a color coded system. So it goes from green, which is good, to yellow to moderate, orange, unhealthy for sensitive groups, red, unhealthy, kind of a maroon for very unhealthy, and kind of black for hazardous. Okay, so you know if you have air quality in the black range, it's not good. I'll just put it that way. All right, and there's various health advisories associated with each one of those categories. Next slide. So this is a chart of all the criteria pollutants and the associated air quality index scale concentrations associated with those pollutants. And so you can see the air quality index scale just kind of normalizes all that concentration data. So next. So right now we're focusing on ozone, and we're focusing in on PM25. All right. And then when we forecast, next slide, we forecast for anything orange or higher. We actually make a forecast daily of the air quality index scale in Pennsylvania. All right. But we're concerned mostly by anything that hits the orange level or higher. So how many of you have heard of an air quality action day? Anyone? Okay, good. No, that's great. This is what this is about. All right. We are concerned air quality action days are issued when it's orange or higher. So in this box, if we think this AQI range is going to be 101 or higher, we're going to forecast an air quality action day. Okay. Next. Okay, so like I stated, we provide daily forecasts across the Commonwealth. We have 4 areas that we provide year-round forecasting for, and 8 additional areas where we have summer-only forecasting, which is primarily for ozone formation. The forecasts are usually distributed by 3 p.m. daily. And if you wanted to get an insight, if you wanted to get our forecast information in your email inbox every day, you can go to enviroflash.info to sign up for the forecast information. Okay. Next slide. These are those forecast areas. And so the solid color line, the solid color shaded areas are the ones that we do year round. The hatched, the lined counties are the ones that we do during the summer. Okay, next. And this is what one of those sample emails looks like. We will give you the color code, the actual AQI value, and a write-up of the forecast for that area. Okay, next. Okay, what kind of tools can we use to get this information? We don't just pull this out of a hat, right? I don't just grab a box of M&Ms because most of these colors are M&M colors, right? I don't grab a box of M&Ms, just eat one and say, oh, that was yellow, I'm going to go yellow today. All right, we actually have data that we pull into the forecast information. And so what are we looking at? We're looking at current conditions. We're looking at the current plot. There's those big blue H's again, right? The big red L's. So we're looking at this kind of stuff on maps. Okay, next. We're looking at what we call sounding data. So we can get this vertical look at the atmosphere over time. Next. And so what you see here is I highlighted in red here is one of those inversions at the surface. And so we know if we look at this little plot here, we know that if the temperature is increasing with height, it's as simple as that. If the temperature is increasing with height, there's some level of inversion there. You'll notice that there's actually 2 inversions. Next. Right there is the second one. Okay, so there's actually 2 inversions in Pittsburgh on this particular day in November of 2020. And finally, next, okay, we're looking at different air quality forecasting tools as well. Okay, so we look at the weather. We also have different air quality forecasting tools that we look at. Next, we look at some other current weather forecast data. So we can look at current observations. We can see wind direction, temperature. Next. Again, we look at the sounding data next. And we can also look at, we have what they call ceilometers. And so what this is telling us is if you see that little red hat, the little red oval there on that image, that is actually smoke that's being picked up by this instrument aloft. So we can actually see the smoke being emitted at some of these sources with this piece of equipment. Okay, next. Yep, right there. Next. We look at satellite data, and so we can take a look at the satellite data. This is in the plains, but we have this for the entire country. Next. And we highlight here, we can actually look at, this is dust that we can see on the satellite that's being witnessed on the satellite imagery. Next. We can also see that's that pink area as well. So we can look at these different products and see what the satellite is interpreting as dust versus smoke and those types of things. Next. Additional, we can look at what they call tropomi satellite. We can actually look at pollutant concentrations in the air. So this is nitrogen dioxide, and the big bright colors, the reddish, that's a lot of NO2 that the satellite is picking up on. Okay, versus the purples, that's very little. Okay, and you notice that a lot of this stuff is in the more urbanized areas, but we can pick up on any given day, we can pick up on individual power plants or any individual source across any of these areas with this type of technology. Next. Yeah, here's another example. Next. Okay, we can look at weather models, right? Okay, so I pulled this morning because I was still doing this presentation this morning. And you'll see that this is actually forecast for next week, okay? And what I wanted to point out was generally in the summer months when we see a lot of prevailing wind directions, we see this pattern where see that pink area over the Caribbean? That's called what we call a southeast ridge, okay? And so we like seeing that type of environment. If you like seeing high air quality, we like seeing that type of environment in the summer months when there's elevated air quality levels across the Commonwealth. But you'll notice that there's a storm out in the plains, or excuse me, out in the Four Corners region at this time. Next. And so we can actually look at a surface model and actually look at the forecasted precipitation on any given day, and we can see that there's this developing snowstorm, at least on one of the models for next week, that could impact us here at the end of next week. So next. Okay, we can also look at, so this is a lot of information, right? So we can also look at photochemical modeling. And photochemical modeling, what the advantage of photochemical modeling, what that does, it not only factors in the weather, but it factors in emissions. And so we can tie in the emissions and weather and try to get some sense of what the air quality is going to be doing. And so these are projected ozone readings. These aren't very high, but this is for today. Generally, we see our high ozone during the summer months. But just to give you an understanding that we have these types of tools that help us inform us of our forecast. So we can look at this type of stuff for ozone. We can look at it for next PM. And so this is another product that we're using. We can see that there's going to be moderate PM25 here forecasted for tomorrow, for instance, okay, for the southeastern part of Pennsylvania. Next. Okay, so those are all the tools that we can use. Now let's talk a little bit about air quality monitoring in Pennsylvania. Next. So the Pennsylvania DEP monitors the air quality in various locations across the Commonwealth. The air quality monitoring program consists of monitoring for the 6 criteria pollutants that I mentioned before, but also in addition to that, air toxics and meteorology. So we actually have equipment out there in the field that actually monitor the air quality, monitor the local meteorological conditions, and also air toxics, okay? And most of the air monitoring setups consist of a station and specific pollutant air equipment at that particular station to monitor the air quality. What does that look like? Well, let me first show you what our network looks like. Next. So this is a map of Pennsylvania. And there you have it. No. This is a map of Pennsylvania, and the black dots are our monitoring sites. The red dots are EPA monitoring sites. And what's also not plotted is what Allegheny County has their own health department. They have air monitoring equipment out in the field. Philadelphia City has their own air monitoring folks that actually deploy their equipment. So we have a lot of monitors right now scattered across the Commonwealth, giving us some indication of what the current air quality is on any given day. Okay, next. Okay, this is what one of our stations looks like. This is actually in Adams County at our Arnsville site. And you'll notice there's a station in the background. You know, we usually have to have a power drop because we've got a lot of equipment operating. And then we have some equipment laying on the outside, some samplers laying on the outside, and also maybe some on the roof, but we also have an inlet on the roof. And that is all getting fed into the inside next. And this is what kind of one of our inside of our shelters look like. This is also that same site and what the inside looks like. And so you can see all the different types of equipment that we have on the inside that are monitoring for different things like ozone and sulfur dioxide and nitrogen dioxide and particulate matter. So yeah, we're really keeping an eye on the air quality across Pennsylvania with this type of setup. Next. If you wanted to get the data at any given time, you're more than welcome to go to our website. I have a link there, and I believe the slides for these presentations, this meeting will be shared. So you're more than welcome to visit our website to check it out. But if we take a look at the latest hourly data link next, we notice that this is what that particular page looks like. So it's broken out by monitoring site. And it just gives us a synopsis of the hourly air quality data that we have coming in. Again, this is from this morning. Next. We can also visit the US EPA Air Now page. How many of you have heard about the Air Now program, the US EPA Air Now program? Okay, you can get your information there as well, because we are giving them our data. We're giving them our forecast information. And so the data and the forecast information that you're seeing on their website is generated from us. All right. And so you get products like this, where you can see the entire country and you can see all the ozone concentrations across the entire country. Next. Or the PM2.5 concentrations. Okay. Next. If you don't like those dot maps, they actually create a nice isopleth map for you. And this was on one high day, I think in November of 2020, at this location in Allegheny County is due to some local industry that's creating some higher PM2.5 values. Okay, next. Okay, so I wanted to give some examples of how smoke can influence both PM and ozone. Okay, next slide. Okay, so this was a big episode back in 2002 of July. These were known as the Quebec fires. And so what happened was you see that there's a thing labeled the low pressure system with all the cloud cover there on the right side of the screen. That was leaving the Canadian provinces. And there were actually forest fires up north of that system. So that system didn't impact the forest fires to the north. But what it did was, what type of circulations around an area of low pressure? Counterclockwise, right? So you're going counterclockwise around that system that's departing Canada, right? You also have a new system moving in from the west. And so it actually funneled this flow from these fires back down across New England and into the northern mid-Atlantic, including Pennsylvania. And so you'll see that you can see the fires there on the image. You can also see the smoke and how that was transported south across New York State and then into eastern Pennsylvania. Next slide. You can see this is another way of looking at it with the same type of satellite. And so the white is more clouds. The brown is actually indicative of the smoke. And so if you look at the shadings of the brown, you can tell how thick and how dense and how light the smoke is actually across much of New England and Pennsylvania at this time. So what does that mean? What did that do, right? It's just smoky outside. I remember walking outside, it was red. Right? I thought it was part of that movie Red Dawn. Has anyone seen that movie Red Dawn? That was crazy, right? Yeah, so I walked outside. It smelled like a barbecue. 7 a.m. It was red outside. It was due to these forest fires. Okay, so what does that do? Next slide. It actually causes spikes in our PM2.5 values. This location, that red line that you see, that peaks up close to 200, that was on the Whiteface Mountain in New York State. So you're seeing a lot of PM being generated from those forest fires in Quebec and impacting much of eastern United States. Next, this was another example. Southwestern California, excuse me. These are some very hot fires. A lot of forest fires were going on back in October of 2003 in Southwestern California. Next. Again, you can see these fires approaching the roadway, but you can see the amount of lift these fires have too. Okay, just because of the heat coming from them. Next slide. This is kind of what it looked like on the satellite. You can actually pull out the hot spots. You can pull out where the smoke was traveling over that time. Next. Here's another view, and this is one of my favorite pictures because you can actually see meteorology taking place. You can see that the hotness of the fire behind the lift of that particular plume, but the smoke is also settling into the valleys in the forefront of the picture. And this is what can happen, right? The fires generate and the smoke can actually settle into the valleys. There's a lot of topography in Pennsylvania. This can actually happen here too. Okay, next. This was 12 noon. And you can see the reddish of the sun just because of the smoke that was going on in San Diego at the time. And all the cars have streetlights on and their headlights on, excuse me. Next. This is the way we used to monitor for PM. We actually had a filter. We actually had to manually change these big filters out. Black is not good. Black is not good. White is more good. So it transitions from white to brown to black. Okay. I know I wouldn't want to be breathing in the black, the amount of PM that was around that area to produce black on the filters. Next. Okay, and then finally, we have one more example that actually impacted us here. This was actually forest fires that were ongoing in Canada. And you'll see here, next slide, this was from 2015. You can see that there again, the brownish area is what you're going to be looking at in these images. That's the smoke transporting into our area. Next slide. You can see it then. Now we're moving into the Ohio Valley. You can see all the smoke there over Indiana and Ohio. Next slide. It actually, much of the heavier part of the plume actually headed off to our south, but it still had an impact here in Pennsylvania. Next slide. And you can see there it's moving off the coast, and that's all due to what meteorological conditions were going on during that time. Next slide. Another way to look at it is this is again another satellite technology. It's using aerosol optical depth, and so what the satellite can do is actually can picture how thick that cloud mass is that it's seeing on the satellite. And so as we flip through here, next slide. You can see the hot colors, the reddish colors is the smoke. Next slide. And you can see here it comes right into Indiana and Ohio next, and it's going to be over Virginia, and then it's going to be moving off the coast next. Great. Okay. So we have an idea of how this air mass was moving in. Next slide. These are ozone concentrations. And so we've had a couple of examples with PM and what the PM25 look like. It can also impact ozone, these smoke events. Next slide. You'll notice that as we go through here, remember, we're looking at orange levels, those orange levels, those red levels. That's what's of concern here, these air quality action days. And so you start seeing more oranges pop up in Indiana, in Ohio. This air mass on this particular day was over Virginia, that smoky air mass. So this is on the backside after the smoke has already moved through and we're seeing elevated ozone levels. Okay, watch what happens on the following day. Next slide. It moves over Pennsylvania and we see a red dot pop up there in Maryland. This is because of that smoke. Next slide. And it really pops the following day and basically lights up the entire I-95 corridor. Okay. Next. We can also look at PM25 data, but the speciated part. So we can break down PM25 and say, okay, how much of it is organic carbon? How much of it is sulfate? How much of it is nitrate, elemental carbon? But there are a couple factors that we look at when we look at this. We look at organic carbon and we look at potassium. And so this first one is actually potassium ion. We can actually see here, if you click the next slide, right there with the red oval, these are the dates in question. These are monitored every 6 days. And so it actually overlapped with this particular episode. And we can see there's a slight little peak, but it's a peak at every one of our sites that we have speciation monitors. And so that's important. We know that this air mass, whatever moved in, impacted PM25 on this particular day. Okay. Well, we also noticed a peak around Independence Day. Anyone know why? Fireworks, right? Fireworks has a big factor toward PM25 as well. We'll get into that in a second. Next, Here's a look at the organic carbon. Again, we're going to focus in on next this particular peak. This is the peak that happened when those fires came through. Next, the smoke associated with the. You'll notice that there are subsequent peaks. The blue area, we attuned to fireworks. In that red area down there in September, again, we can get hit with multiple types of these episodes every year, where smoke is impacting both ozone and PM2.5. Next, and again, these are the forest fires and the fireworks that we saw that particular year. Okay, next slide. All right, that's it. That is it. So yeah, a lot of information, but I wanted to give you guys a good sense of, okay, there could be air quality impacts associated with these fires. I know we were talking about forest fires a lot, but we can see what the impact of fires in general could have toward air quality, right? And how weather can play a role too. All right, so I thank you for your attention. Do I have any questions? Everyone's asleep. Yes, question. Perfect. If you don't mind stating your name and then your question, that'd be great.
Travis Weinzerl. The question I have is, most of our prescribed burns occur during the spring season.
Okay.
Most of your air quality episodes or higher concentrations of particles tend to occur in the summer, correct?
Yes.
So are there particular days during the spring that we should be more attuned to,
Okay.
where it's more likely to impact air quality negatively?
Well, okay. Let me redirect the question back to you. Okay, or anyone in the room. When you're actually doing prescribed fires, what precautions do you guys take place? That do you look at the weather? Obviously, you're looking at the weather. Do you look? What other things are you looking at? Like, are you looking at high winds, low winds? You know, what are you looking at? I'm just curious.
Generally, you're looking at low winds, clear days,
Okay.
lower RHs,
Okay.
for at least from a Pennsylvania standpoint.
And that's what you're looking for. Are you looking to burn on those particular days?
Those are the days we're looking to burn.
Looking to burn. Okay.
So smoke in the air those days.
Yeah. And so, I mean, I was showing you a map of our air monitoring network, right? And so we can see on occasion some of the impacts from these prescribed burns on those particular days, because that sounds a lot of like what we see for when we're looking for higher quality days, right? With the clear skies, the light winds, right? And so we can actually see some of those depending on how close in proximity those particular prescribed burns are happening toward our air monitoring sites. We can actually see some of those impacts at our air quality monitoring sites, because of those are the same factors we're looking at when we're looking at these types of events. We don't see a lot of air quality events though in the spring because of how unstable the air is at that time. You know, that's usually the peak of our thunderstorms. You notice that a lot of the thunderstorms are occurring right from April to June across Pennsylvania. There's a reason for that. It's because you're transitioning to a warmer air mass, right? The summer is a warmer air mass than the winter. Okay. And so it's this clash of these, what's remaining of that cold air combined with the warm air that's trying to build into the region develops these thunderstorms. And so with these thunderstorms, you're going to get a lot more mixing, a lot more wind. And those are the types of environments that don't lead to higher pollution events and not what you're looking for directly when you're doing prescribed burns. Okay. Great. Good question. Anything else?
Thank you.
Okay. Thank you. Any other questions, comments? Anything? Great. All right. Thank you. I appreciate it.